Hello, my name is Steven. Together with Anton from Mindstorms Hacks, we developed a hardware breakout board that makes it more easy to connect different kind of sensors, non-Lego sensors, to your Lego Mindstorm hubs. The board is based around a microcontroller called ESP8266, and it supports Wi-Fi and is connected through its UART to the Lego Mindstorm hub. I wrote the library to make it more easy to communicate with that board from within the Lego Mindstorm hub. In this tutorial I will show you how this library works and how you can use it. Suppose you have on your breakout board, you have connected some sensors or some displays or something, and you have written some functions to drive these displays or to read out the sensors. Now you want to initiate it from the Lego Mindstorm hub. You want to call a function remotely on the ESP module. And if the function gives back some value, you want to read these values as well. This is basically called RPC, Remote Procedure Call. And the library is a lightweight RPC library. And it's written in such a way that it runs on one side on the ESP8266, but also on the OpenMV H7 camera. And the other side it supports all three Lego Mindstorms hubs. What I will do in this presentation, I will give you a short overview of how this UartRemote library works. Then I show you how to get started, how do you install the library on your different platforms. Then the third part, we will go a little bit more in more detail about how the library works. And I finalize in the fourth part with a small demo where we will drive an OLED screen from a Lego Mindstorms hub. So to give you an overview of the UartRemote library, I hooked up the ESP module to a Spike Prime, and on the left hand side you see the web REPL prompt of the ESP module, and on the right hand side you see the REPL prompt of the Spike Prime. So you can show what kind of platform is running. So this is the Spike Prime. And this is the ESP8266. So to start with the library, we need to import it. So I import all from UartRemote. And we do that on both sides. And to instantiate, basically the library consists of one class, UartRemote, and you need to instantiate that class. And on the Spike Prime, you need to define on which port you connect the ESP module. In this case, I connect it to port A. And on the other side, you need to do the same, but there's only one UART on the ESP module, so I don't need to give it an argument. Now suppose on the ESP module you have some sensors or some LEDs hooked up, for instance an LED, and you want to drive this LED. There's three colors, so this function would give some code to drive this LED. In this example I only print the three values. Suppose you have another function that reads out an MIU. For instance, it reads the acceleration sensor. The three vectors of the acceleration, and maybe you have a function that has two arguments and returns another argument, and this is the sum of these two input arguments. So now comes what you would like to do is from your Lego Prime, you would like to call one of these functions. And this is where this library will be helpful, because I can define our commands on this side. And the command is just a text string, and it's easier. The most easiest thing is to give it the same name as the function, and you connect a function to that command. In this case, it won't give any results back, so this is okay. Let's define the second command. It's the MIU. The corresponding function is MIU, and now it gives back a float vector, a float list. And the third command will be the add command. The corresponding function is add, and also this one gives back a single float number. So this defines 3 commands on this side, and I can start a loop, and in this loop it will wait until it receives one of these commands, and it will execute the corresponding function with that command. And if there's a result of that function, it will send it back. So on this side, on the Spike Prime side, I can send a command and receive the result of the command. So in this case, I send the command LED, and I have to pass 3 values because the RGB values, so these are 3 unsigned integers or unsigned bytes, and I can define the bytes here like this. And you will see that if this command is being sent, it is received on this side, it calls the corresponding function and it prints these 3 values that I pass with the command. I can do that multiple times. So let's call the second function, the MIU. That function doesn't need, that command doesn't need any arguments. So I don't need to specify anything else on this. And now it immediately returns the value that this function returns. And let's execute the third command. So that's the add command. I have to pass 2 floats like this, and now it will return the sum of these 2 values. To show you how fast it works, I just can add 100 numbers, for instance. So I add 1.1 to I, and it will run until it's 100, of course. So this gives you an overview of the communication between, in this case, the master, which is the Spike Prime, and the slave, which is the ESP module. The library is written in such a way that it can also be exactly the opposite way. So that the ESP is the master and the Spike will be the slave. So this is the second part of the tutorial where I will show you how to install the UartRemote library on the different platforms. The first thing we have to do is to clone the repository from our GitHub project, and then I will show you how to install the UartRemote library on the ESP8266 Wi-Fi board, on the Spike Prime, and on the EV3. So let's get the GitHub repository. So I can git clone the repository, and now you will see that it's exact copy of what's online. And in the libraries, UartRemote, MicroPython, there's the UartRemote.py. To connect, to put it on the ESP8266, we use the web REPL prompt. So I take the browser, I choose the file. In this case, it points to the MicroPython UartRemote library, and I send it to a device. It's now sent, and to see whether it's on the device, I can import OS, and I can OS list there, and you should see the library that is there. I can try it. See whether it's working. It seems to work because if you try this, then it's working. Now there's one thing that is in the default settings of the ESP8266 MicroPython. There's a REPL prompt on the UART interface, and that REPL prompt will interfere with the communication of the UartRemote library. So we have to disable that prompt first. So what you can do is you can get a file, the boot.py, from your device, I already done it, so then I will open up Visual Studio for that boot.py, and you will see here there's a line which says US dep term. There's a comment in the default way, so I uncomment it and I add these two lines, and that gives you the chance that if you boot the ESP, that you have 5 seconds left to get into the REPL prompt on the UART, in case you lose from some way or some course you lose the web REPL connection. So I add these two lines and I uncomment this line. Save this one. Now I can choose the downloads. I choose the boot.py and I send it to a device. Now it's ready. Now I need to reboot the ESP module to get everything running. So now let's move over to the Spike Prime. So the Spike Prime is a little bit more complicated to get a file uploaded on the Spike Prime. And the first thing you need to do is to find out what your serial port is on your system. Typically they look like this. On a Linux system it's usually /dev/tty and then USB 0 or ACM 0. On Windows it's a COM with a number 1, 2, 3, 33, and the Mac OS it's something like /dev/tty USB modem and then a number. So you have to figure out by reconnecting it and look in the /dev directory. I can show you briefly. So if I look here, I see that there's a dev/tty ACM 0. So that's the one I need. So then you need we use a tool which is called RShell. RShell, you can copy files to and from the Spike, and you can run the REPL prompt. So you can install, there's a Python program, so you install it by pip3 install RShell. I already installed it, so it probably gives that it's fine. You start it up, you go to the directory in which the UartRemote library is residing. You start the RShell, and now I have to connect to the Spike. So I do this with connect serial, and now I type this serial port that I figured out. You will see that it triggers something, and now it says it's connected. And at this point I can copy the UartRemote directory, UartRemote library, to the Pi board. This is the Pi board. That's the root of the file system on the Spike. If I copy it there, it will be there. I can start a REPL prompt, and now I can try whether I can load this library. Oh, import. So that works. It seems to work. So that's just fine. So now we uploaded the library on the Spike Prime. If you will use the normal IDE for Spike, you also can import the UartRemote library as well. And it stays on the device even if you reboot it. So finally I will show you how to install the UartRemote library on the EV3. For that we need to connect to the EV3. Of course you have EV3 dev running on it. How to do that you can find on the internet. We will open an SSH terminal, and then we will find out the IP address of the EV3. Once we've done that, we will copy the UartRemote.py library using the SCP secure copy command from a command window on your local system. So let's do that. So I can go into Visual Studio Code. Already connected the EV3 device. I open SSH terminal. Now I have an SSH, I have a terminal, a Linux terminal on the EV3. I'm in the home directory of the user robot, and what I need to figure out is the IP address of this device. So I type in IP address show, and then of the device USB 0. That's the device to which it is connected, and you will see here that it's 10.42.03. That depends on the settings of your EV3, of course. Now I can go to a terminal, and I move to the directory in the GitHub repository where the UartRemote.py resides, and from there I started a secure copy of this UartRemote to the username robot at 10.42.3, and now the directory is home/robot. You might have a subdirectory there where your project resides. In this case I use EV3 test. And you will see that the file, it asks the password for user robot, and that's maker, it's a default password. And now it copied the UartRemote directory to the EV3 test directory on the EV3. So if I go to the EV3 test and I look inside, I see there the UartRemote.py. If I start a REPL prompt, pybricks REPL, I can try loading the UartRemote library from UartRemote import star. Let's try it, it's working. I connect, for instance, port S1, and it seems everything is working. So at this moment you have on 3 devices UartRemote library loaded, and you can start using it in your projects. So let's look a little bit into more detail into the library. Before we start looking at the commands of the library, I will explain briefly how the packet format is defined. So when we transmit a packet using the UartRemote library over the wire, the following packet format is used. It uses a delimiter to start with and a delimiter to end the packet. These delimiters are used for checking a correct reception of the packet. Then the first byte is the length encoded in a single byte of the remainder of the packet. Then the command is sent, but to know how long the command is, the length of the command is also encoded in a single byte. Then the length of the format string is encoded in a length in a single byte. Then the format string, and the remainder of the packet is used for the data that is encoded according to this format string. And we will look into more detail how this encoding works. But basically, if you know how struct pack works, then you get an idea of how this format string works and how the data is encoded in a binary format. The UartRemote library has these basic methods: encoding, decoding. These are the underlying methods for creating these packets and decoding the packets. Send, receive, sending on the UART. Send, receive is a combined function, and these we will look later on in more detail. And then there are 2 commands that more or less shield the user for implementation details of the different platforms. So you can call this to see if there's a byte available, and this to flush the reception buffer. So the encode method takes a command and a format string and data. I will explain this briefly, and then I will show you in an example, and I think it is quite clear how this works. So the format string can be a B for byte, or I for this should be a small I, capital lowercase I, a float for float, and S for string. And these format characters can be prepended by a number, for instance 3B2F, that means 3 bytes and 2 floats. If you encode a list, you only have to take one single character, and with that single type all these elements in the list are encoded. And the same goes for a string. You only need one S for the whole string. So let's see how this works. So I have here a REPL prompt on the Spike Prime, and I have this. I have a web REPL prompt on the ESP module. So let's load the library on both sides. I initiate it on port A, and here I initiate it on the default UART. So let's try this encoding function. I don't need both sides, but let's do it on the ESP module. So if I encode, the first argument is the command name. I can type any string I want. It's a command. Then the format string, for instance 2 floats. And then I need to pass 2 floats as an argument. And now I see the packet format, and you won't see in this case the delimiters, because these are only added to the packet when it's sent over the wire. So this is the packet without the delimiters. If I now decode this packet, I will get the same as my input. So it sees the command and it gives a tuple with the arguments that I sent to it. So for instance, if I want to add, for instance, 2 integers to that, now you see that it has added 2 integers. I can also encode an array, for instance, or a list. Suppose I want to encode a list of unsigned bytes. I can take any list. If I decode it, it sees that it is a list. So it decodes these binary data to a list. The same goes, of course, for a float. You will notice that the float takes more bytes to encode a single number, of course. But if I decode it, you just get the float numbers. For a string, it is actually the same. So I can encode a string, any string. And if I decode it, I get back the string. I can also combine it with, for instance, 2 bytes. So this would be useful if you would write a string on a display on a XY coordinate, for instance. Now I get the string back and the 2 coordinates. So this works fine. So the send function, I go back to my slide for a moment, is basically the same. It calls immediately the encode function, so it takes exactly the same arguments, but the difference is that it writes the encoded result of the UART. The receive function is actually the same as the decode function, as that it gives back the results of the decoded packet. So let's try. So I would say receive on this side. So it waits until it gets a packet, and on this side I will send, for instance, instead of encode, I will send the same packet. Now you will see that instead of decoding it on the same side, it receives it on the other side and decodes it there. I can send something back. For instance, to F. I have to set a receive on this side, send it, now it sends it back. So you can send back and forth this kind of commands. If you would only have these functions, these methods at your disposal, you would need to map the commands on specific functions, and that's the next thing that we've implemented in the library to help you doing that. That's the add command method. The add command takes a command string, it takes a function that you want to map on that command, and if the function returns, or it should be has no return arguments, then you just need these two arguments. If it returns, for instance, 3 floats, you have to define the same way as you defined it in the encode function, the format string here. If it returns a list of floats, for instance, you only have to take a single character. So let's try that. So first I need a local function. So I already have shown you how this works in the overview, but we can now go. No, I don't return anything. I just print colors RGB. Okay. Now I add this command to this object. So I say LED, LED. Because it doesn't return anything, I don't need to specify the format string here. If I now look in the class, there is a command dictionary, and there you see the mapping of the command name to the function. If I have this function is the same as to which this dictionary points to. There's another parameter, that's the format string, and the format string is empty because it doesn't need to format anything because there's no return address. If I define, for instance, this add function again, where I return the sum of A and B, if I would define that, I need the command name, the function, and now I need to specify the return format. So this is a single float. If I now look to these, now I see that the add function, the add command, has a float as a result. And of course, if I look at the commands, you will see that the mapping of the add command is to the function add. So now I can do a single wait and wait for command. So it waits until it sees one of these commands and it will call it. And on the other side, I hope it's still alive, I can send and receive a command, for instance, LED, and then there's my 3 parameters. But I have to define what kind of 3 parameters I specify, so I say 3 bytes. So now it just processes one single command and returns. So this can be used if you need if you make your own loop in which you check for commands. If you want this done in an endless loop, you can use the loop command. Now every time I send it, it will go back and wait for the new command. So if I take another command here, for instance, the add, I send 2 floats. I get the sum. So I can use these 2 functions. Another thing to note is that every time you get an acknowledge, and it might seem a waste of time or a waste of usage of data, but it's a good thing because the sender has no notion of how long it takes for executing the command on the remote side. And it will get back an acknowledge if the command finishes. So this is blocking in the sense that it has to wait for the acknowledge, but it helps you to prevent sending too many commands at one time. If I wouldn't send the acknowledge, this side wouldn't know whether this command already has finished, and you would probably get an overflow on your receiving queue on this side. So that's the reason, although there's no arguments coming back, it sends acknowledge. In this case, of course, it's acknowledged, but it also sends back the result of my function here. Now we've implemented, I don't know whether it's working, but this loop seems to be quite difficult to break, because the wrap REPL is not, I mean, the loop takes all the resources, and that doesn't give back the wrap REPL a chance to break in. So what we've implemented in the ESP is a hard interrupt request attached to the boot button. So if I press this boot button a few times, you will see that it breaks the loop. So that's quite easy to use if you are debugging or if you are manually executing this library. So I think I have shown you the basic commands of this library, and it's up to you to make nice applications with it to drive sensors or screens or whatever, and use this library. Another thing is that if you look into the source code on the GitHub, you will notice that I'm not a professional Python coder. So if you have any suggestions or any additions or any comments, please leave a note on the GitHub in the form of a pull request. Or if you don't want to send a pull request, you can maybe leave a note in one of the social media channels of Anton Mindstorms Hack, which you can find in the description below. So have fun, and I hope I will we'll hear from you. If you made a nice project with this library, please let us know. So this is the final part of the tutorial, where I'll show you a small demo using an OLED screen that we drive from the Lego Spike Prime to the ESP board. If I show you how I have hooked it up. So you see here the screen is a 0.96 inch screen using an SSD 1306 controller. It's connected through the I2C. It's the Grove connector, which you see here on the connector board, and the connector board is connected, of course, to the Wi-Fi module, and that is connected to the Spike Prime over here. So first let us look at the code that we have written as a project. In the project folder of the GitHub you will see 3 files, one running on the ESP, one running on the EV3, and one running on the Spike. So let's start with the ESP code. So we hooked up LCD OLED screen on the I2C bus. If you hook up any devices to the I2C, it's always a good idea to check whether the I2C is working. Oh, I didn't select it correctly, probably. So I copy this. So I have to initialize the I2C bus. You have to define the SDA, the data, to pin 4. That's how it is connected in our board, and the clock pin to pin 5. Now I can run I2C scan on the bus, and it will scan for all devices on the bus. I hooked up just one device that has address 60. So this gives me the guarantee that the I2C is working for this device. So it's always a good idea to do this first. If you look at the code, the nice thing about the screen is that the driver for the screen is already incorporated in the MicroPython distribution that we are running on this board. So you don't need to install any libraries for that. Once you initialize the screen, we use this object here, OLED. You can use methods like text, show, fill to drive things on the screen. We put all these commands in a class, and these methods can be called from that class. What we do then is we use the UartRemote library to map all these commands on these methods. The reason that we use a class is that the state of the screen needs to be stored in the object. Otherwise, the screen is initialized, but you can't access the initialized screen anymore. So this is the reason we put this all in a class, and we map all these different commands to these different functions. And depending on the parameters that you give to these commands, they will be mapped on the specific parameters in the methods. And then after adding these commands, we just start a loop in which the ESP is waiting for one of these commands and executes the corresponding function. So you look at the OLED spike program on the spike side, and there you see that we also use a class to put all these methods in, driving the display. We hide actually all the commands that we defined earlier on the ESP side within these methods. So the only thing you have to do is on this spike is initialize your OLED object, and then you can use just OLED methods as if you have hooked up the display locally to the spike, but actually it's running on the ESP, and all these commands are being transferred using the UartRemote library to the other side. So this gives a good example of how to hide all this functionality for the user who only has to do these simple commands. So let's look how this works. So we first have to upload this code to the ESP and to the spike. I will show you how that works. The spike has switched off, so I have to hook it up. So I have to connect. Maybe it's already connected. No. Connect serial. So it's connected again. Now I can copy. I'm in the OLED directory, so I can copy the OLED spike code to the PI board. On the other side, I have to see whether I can connect to the ESP module. How this works, doesn't work. Maybe it's not connecting. Okay. There it is. Log in, and also here I can upload the code. I'm in the OLED project directory. I take the ESP code and upload it to the device. And now I can use this demo code here. What it does, so it initializes the class and it waits for this loop command. So it waits for a command to be run. The other side, I go to the REPL prompt, and here I do exactly the same, but then with the spike demo code. No, let's look what happens. Let's look what happens on the screen. It's still black. So if I execute this command, you should see a string. You see, this is cool. It's a little bit flashy, but it's flashing because it interferes a little bit with the light, I think. So is the camera. But this is working. So now we can experiment a little bit further. For instance, we have here this OLED class. So I can immediately show you, for instance, what happens if I wipe the screen, for instance. So I fill it with zeros. I have to show it. Only then you will see what you. So now I show it. It's wiped. So let's try, for instance, a loop where we scroll some text. So I take a range of, let's say, 60. I fill the screen, I clear the screen, I put a text like hello there, and I put that on the coordinate like 10 and then I. So the I increases, so the Y coordinate should also increase. And then I have to show the screen. No delay, so the speed you will see is the speed with which these commands are communicated to the other side. And you get an idea about how fast so let's try this. There it is. You see that it's scrolling down. And the speed is quite satisfying, I think. If you measure the speed, it's about something like 30 commands per second, back and forth, so inclusive the acknowledge. So this is the OLED demonstration. I hope you get inspired in using this UartRemote library for your own projects. If you have any additions, any comments, or any suggestions, please, you can send a pull request to the GitHub or reach out to us on one of the social media channels of Anton's Mindstorms Hacks. Thank you.